Okay, you guys, we're back for another edition of 5114. Looks like we've got a couple customers live. Sierra will kind of be checking in, see if any questions appear. So if you want to interject something, do it over the chat forum. And we'll have the high-res videos up later in the afternoon. Sorry for the technical glitches and having to combine two lectures. I think I have that problem tracked down. I'm not 100% technology. Saying that, I do have workarounds now that can work. Last night, I was having a lot of difficulty uploading everything. So it seems with everybody in my neighborhood watching Netflix, the uploads can take anywhere from 2, oftentimes 3 hours, and yesterday took about 12 hours to get everything uploaded. So anyway, I appreciate all the flexibility. We'll try to keep the quality of these videos and pseudo discussions going. Midterm is coming out. I'll have that to you in Saturday afternoon or something. Don't worry about when it's due right now. Don't worry about all that stuff you guys normally worry about. Let me do all that worrying. This is a new format. So what I'm going to be doing is I'm going to be asking you some questions, and what I think I'm going to ask for, and I don't know how many questions I'm going to ask, I don't know what I want you really to focus on is, do you know this material deeply? And so are you able to ask yourself the right questions? And sometimes midterms give us an opportunity to check everything. Did you get a fundamental? And so I want to make sure you don't miss the fundamentals in here. So I'm going to be asking you a series of questions. Might even seem psychological at times. Do you know how to prove this? Could you prove it to this level of detail? I'm just trying to figure out what's the right way to ask you those questions. I want to be able to check if you're way off as well. And so I'm going to probably be asking you for solutions, like just tell me the solution. And it might be in terms of multiple choice. And so if you know the answers, and you're confident, and you know, and you've asked yourself the right questions, because I've asked you the right questions, and you know whether or not you know how to prove everything rigorously. Could you demonstrate it? I have this theory, we always know that. You know, could you explain it to somebody is really what we're asking. It's hard to do. So, you know, anyway, I'm improvising on the assessment in here, so I'll try to be really flexible with you in terms of deadlines and all of that. And so we're trying out new stuff. So anyway, hopefully that alleviates some of your anxieties. Maybe it creates more. So that's also a good thing. That's one thing I really liked about midterms, is that it kind of worried you enough to try as hard as you could. So let's try to keep that mentality, but don't worry so much about what your grade's going to be, what the format, all of that. I'm going to be flexible on everything. Okay, today, switching gears, decision theory. And so we've been talking about a lot of choices that we make, bias and variance and things like that, and what are we trying to reduce. And I want to formalize that a little bit more. And so this is statistical decision theory. There's, you know, other types of decision theory out there, but they all basically deal with utilities. And so in economics, you're trying to maximize a utility, whether it's social welfare, the economy, maybe health, something like that. There's trade-offs that you have to make when you do that. We're learning all about that. In statistics, we usually phrase this just a little bit differently. We talk about our losses, how much we're going to lose, instead of trying to maximize our utility. And those are inversely related to each other. And very similar concept that you would see over in other fields. I will mention that this branch of statistics right here, the very formal, you know, sort of branch of how close are you to the truth and how are you going to discount yourself when you miss? This has persuaded a lot of people to operate differently. This might be the thing that tells you how you want to operate. So whether it's extreme valuist, you like looking at extreme values of things, or if you like looking at things on average. And so those are very different measures, you know. different criterion, and it might steer you into different directions of inference. So I like this conversation. We're going to talk about a lot of different ways of doing this, Bayesian and non-Bayesian ways. Let's just start out with this concept of loss. Then I'll tell you about risk that's related, and I'll show you in a special case what the bias variance trade-off is all about. So decision theory. So let's just get a little bit formal and define a loss function for ourselves. So loss functions. And I'll say my loss function is L for loss function. And it's going to measure the difference between the truth. I'm going to write down the truth, theta, and what we guess the truth to be. I'm going to call that theta hat. Okay, so this is our guess at the truth. And so we want to quantify the difference between these two things. So we're thinking about distributions still. Some distribution, we'll call it fx given theta. And so we get to see data that comes out of all this. Independence or dependent, same theory that we're going to apply to everything. So we have some model, we get to see data, we want to know the parameters. This function right here is going to be a measuring stick of sort for us to measure how far away we are from the actual truth. What's the difference between these two things? So I want you to be thinking about this maybe in high dimensional space, but I'm going to be writing out examples today just using one-dimensional stuff. And so, but really what this is this is just a positive function that measures the discrepancy between your guess and the truth. So I'll remind you right here how you guessed is you use data. And so I'm going to say this is a function of the data that we get to collect. And so I'll just write this down also as EX. So this is an estimator, often denoted as your parameter with a hat over the top of it. And it's a function of the data. This is your data. That's what you get to see. And so I can write this just a little bit differently. If you want me to write it mathematically, we might write something like this. L theta hat given theta is a positive function let's just write it like this, is a mapping from 0 to infinity. Okay, so just some basic functional notation. All this says is it takes these two things in and it gives you some positive number. The idea is that the farther away this is from that, the bigger this number will be. This is really just a norm on something. So AKA norm. Of some sort. So let me give you a couple examples. These are your typical examples, and this is the hardest stuff to come up with as a statistician. So as a professional statistician, when people are trying to tell me or trying to ask me what their decision is going to be, I'm always asking them, what their utility functions are. How much does it mean to you if you're wrong? And so here are some conventional choices. Oftentimes, if you're operating in the world of competitive prediction, usually in something like a Kaggle contest, they're going to tell you how you're going to be scored. And they're going to tell you how much you're going to be discounted when you're wrong. So, conventional choices for this, and depending on your application, you might have to tailor these, change them. This is going to be squared error. We'll write down mathematically what that means in a second, but it means what it says. Absolute error. Or 0, 1. I'll call this loss. You could say error as well if you'd like. So let me tell you a little bit more about squared error. Looks like this. Theta minus theta hat. Squared. So the error is on the inside and I squared it. And that's my loss function. So for absolute error, just like what we said, theta minus theta hat, absolute value. 0, 1, it's going to take an indicator function. It's going to look at what the truth is. You write this just a little bit differently. So indicator function, it's going to take in whatever the truth is. So that's theta right here. And it's going to see if it matches that. Now if you've matched in the typical notation, this is a 1. And if it's anything, theta hat is anything other than theta, it takes on a value 0. Now we want the loss to get bigger when we're wrong. So I just need to take 1 minus that thing. And so when I'm right, this takes on the value 1. That's 1 right here. So I've made no error, I incur no loss. Or if I'm wrong, this will be 1. So it's an indicator, it's a switch. And in typical problems, you might be able to encode things using different indicators and encode different levels of losses. So you could replace this from 0, 1 loss to something with categorical losses. So if you knew how to encode that. These are, of course, popular choices because they're easy to work with, easy to understand. So usually in regression, we adopt that loss. So if you have a lot of outliers, this loss function is not a very good choice. So because everything's going to get steered by extreme value. So as these get farther and farther apart from each other, that value gets quadratically larger. And so you might say, hey, we don't want to penalize the losses that much. And so this puts less penalty on extreme losses. It treats everything linearly. And this is just categorical. So either you got it or you didn't. So a lot of times people are asking me how I'm going to grade stuff. And so I'm not sure what my loss functions are going to be for this midterm, but it's not going to be any of these. I usually joke around about this one, that either you get it right or it's wrong. So I've got to be 100% right or it's wrong. And we've all seen people do this before. You may have been unfortunate in having an advisor or a professor like that is so nitpicky, they won't take anything but perfection. Very difficult when you're in those environments. And so, kind of like this stuff always just feels right. It's harder to compute with because of this absolute value sign. So sometimes people want this stuff and it's harder to compute with than that. This has an obvious benefit. You can do calculus with it. And so it's smooth. So I'll just give you a couple other names also. This right here is the L2 loss function. And this is L1 loss. So if you ever hear people use those terms, they're really thinking about this power over here. Okay, so there's something called LP loss. Okay, so of course, to use this right here, I'll remind you, this is a function of the data. I need to plug in my data and then see what I've lost. Now this is a purely theoretical thing because I don't get to know theta. And so this is something you get to conjecture at. For particular thetas, how are you going to incur loss? So I want to just remind you, this is what you do every single time in a simulation study. You know what the truth is, you generate data, and then you measure how far you are from the truth. And so in simulation studies, you're basically concocting this whole setup. Now, of course, we have to plug in a particular data set. So this is a fixed data set. And this is going to change. Every time we see data, we incur some different loss. So where this is useful is trying to a priori think about which methodology you want to use when you go and you try to forecast what the truth is, theta. And so depends on what theta was in the first place. But ultimately, what we're going to use this framework for is trying to decide which estimators we want to use in the first place. And we're not sure which data we're going to get in the first place, in the real world. But presumably, we know characteristics of the data. And how those characteristics depend on theta in the first place. So what I want to say is, instead of just using this on its own that changes on every data set, you might want to use this framework to analyze how good are estimators when I know how the data is generated and how that depends on theta in the first place. So I'm just going to write that out. So on average, we'd like to know how good our estimators are. So instead of just using this framework to say, here's how wrong you are, this is really asking you to decide on some notion of your wrongness, how much you think it matters. If you were working with a real utility, you could probably characterize that. I'm not sure in just the mathematical sense when it's like, well, when I pick that the answer is theta, or I think that the answer is this value and I'm 17 units apart from it, I'm not sure exactly that I would know how to penalize myself. You have to tie it to something that's important. So otherwise it's just, I'm 17 units wrong. What does that mean to you? And so this is forcing you to think about that. So do you want to penalize yourself extra hard when you are very, very wrong? And this is what this says. And you could penalize yourself even harder than that. But once you have this notion of scoring yourself, you can use it to figure out which estimator is your best guess on average. So no guarantee that you're going to be right every single time, but on average, you can maybe say something about that. So I'm going to write this down. So that means we want to look at the on average thing. So I want to look at the average performance of our estimator. And so what am I going to average it against? Well, probably how likely that data is in the first place, and how that depends on theta. And so we have something for that. That's this. So this is your averaging weight. So it's how likely you really are to see X. I want to account for that in my averaging process, and I want to account for whatever the truth was. The specific context, where theta is that number, what does the data look like? And to do this on average, I integrate over this. Oops. Got a little bit of an issue. It's not just EX. It's how EX relates to truth theta. Right here. So let me just say that again. We want to look at this thing right here, our loss between these two things. And I want to average over this. So sorry for saying that so clumsily. But this is what I was thinking about. So this is my weight. How much we believe X will happen given theta. So there's a presupposed truth. And to average over this, we just need to integrate. So that's our averaging mechanism. Let me say that just a little bit differently. Sierra was asking a question. She says, should that be theta? Well, just keep in mind, I don't have any right to integrate over theta right now. So theta is fixed. So there's a presupposed truth in all of this. So just to recap, there's some truth. We know how data tends to look, or distribution, and we're just averaging over the losses for a particular theta. So again, I kind of think of this as just like what we do in a simulation study. So if you remember what you do in a simulation study, is you just keep simulating data out of this, and you measure your losses. And then you keep track of whatever that norm is. And you do it over and over and over again. This is the thing that does it an infinite number of times. So this is the thing that you're really trying to approximate. And so this has a name. So this creature, integral, loss between our estimate and theta averaging over different data sets, an infinite collection of those. This is your whole data vector right here. This has the name, this I can interpret. So as a statistician, I write it down like this: expectation of the loss. And I dropped the notation for X right here. I've integrated X out. So I'm really just looking at how much loss we expect to have using that particular estimator. For, and I'll remind you, guessing theta while using estimator E. And the data is being integrated out. So this is expected losses. That's all it is. There's another name that sometimes you encounter first for this. So some people start you here, but I've taken you down the other pathway. This is called risk. And if you want some notation for that, you could say this is the risk of using E, my estimator, on average, when trying to figure out what theta is. So that's called a risk function. So I would argue that what you're often trying to do, or I should just, this is a risk function, and I'll just make a note that it's a function of theta. And so for different thetas now, this is going to incur different expected losses, aka risks. What I'll say is when you're doing simulation studies, you're trying to draw this curve for a particular estimator. And then you change your estimator and you draw the curve. And you see how it looks. So when I see this setup, I just think this is what we're always trying to do in a simulation study. This is the mathematical lens that we're trying to look through. And if you could do the math, you wouldn't have to do the simulation. There's a lot of practical cases where you can't quite do all of the math, and you have to put in simulations. Okay, so we have a bunch of notation. I want to look at an example. Just to tie it all together. Lots to be said about this framework. Here's an example. Let's say I've got some data. It's coming from a normal distribution. I'd like to know what mu is. And I'm going to make my life easy, and I'm going to say I know sigma squared. If you didn't know sigma squared, you can apply all of this theory to both parameters simultaneously. Just define what your losses in each one of those parameters would be. Okay. We get to see n data points. This whole thing. And so I might ask, question, here's my setup. Under scenarios like this, I might be asked to estimate mu. This is a simple problem. We have answers to it, but let's just apply our theory and see if this theory starts to solidify why our answers that we keep going back to are good. So question, how do we build an inferential procedure? So I'll say, just make this simple. How do we come up with an estimator for estimating mu? That's what we're going to try to do. So step one, define your losses. And this is going to be, I would say, in any real problem, this deserves your attention. And it's not a question you're going to be able to answer just by yourself. So I'm going to make an arbitrary choice. I'm going to choose the L2 loss function. Now you might say, that's not arbitrary at all. Lots of people use it, and I would agree with you. So maybe I'll use it because lots of people use it. That doesn't sound too convincing. But I don't want really big answers. I want to penalize myself really poorly, really hard when I'm very wrong, and this does that. There are some repercussions to doing that, saying that if you were Newton or somebody like that, way back as all this was being concocted, if you were Gauss, you like this because you can do calculus. And so everything is smooth. So a lot of our utility functions, log utility functions, squared error loss in this case, they're picked for arbitrary mathematical reasons. Arbitrary meaning that it makes the mathematician's life a little bit easier. There can be other good properties though. And so maybe this isn't arbitrary. You can decide, but I've had a lot of people say to me over the years, this is the natural choice. And that I'm a little hesitant to accept. It might feel natural because you do it all the time, and other people do it. But I wouldn't say that there's anything particularly special about that just on its own. Saying that, I've got these in my hand right now. And so the only problems I can probably do, are problems that are smooth, because I can do calculus. Okay, so the goal, if we agree on L2, we want to find an estimator. So some function E that takes in my data, and I'll just leave out the data because that's not the important part. I want it to work on average, such that this criterion right here, expectation of the losses between E and mu, are minimized. Okay, so we want to just come up with this thing where it's minimized. And this thing, because I make my life easy, I can write this down pretty easily. So this is really just the squared difference between E and mu. And I want to minimize this thing over that function. And so that's the name of the game. So we can solve this problem. But I want to just show you something that this has a nice decomposition. So let me just write it out like this. This is the expectation of E minus, and I'm going to plug in a funny form. Let's actually, this is the thing we're taking the expectation over, is EX right here. So this is operating on X. Let's plug in our data. This is our averaging mechanism. So this is going to be X. And I'm just going to add a funny form of 0. And if you ever worked in a squared error loss, this is always going to work for you. So people ask, how did you know to do that? Well, if you've done it once and it worked once, it'll work every single time. And so after this, you'll know, just do this. And it turns out answers center around the expectation in the squared error loss. So just a little bit of illumination on where we're going. Usually when you're working with squared error, you like expectations. So I'm going to add in this funny form of 0. And that's all squared. I'm going to put some braces in here. So now I have two things that I'm going to look at, and I'm going to square this out. A lot of you will know the cross term will cancel when you do this. We'll show that. So this is going to be EX minus expectation of EX squared. There's another squared term over here. I'll just put that in first. That's the expectation of EX minus mu squared. And the cross term is just right here. So this is going to look like EX minus the expectation of EX times this thing. Expectation EX minus mu. So I've just expanded the square, and now I can start to slide my expectation over all of this. I want you to become aware, real quick, that when I take this operator and I start dragging it over these three terms, it's a linear operator, so I can break it into three different expectations. When the expectation comes over this term, right here, it turns that thing into the expectation of x. This is the only random bit in here. So this is the only random thing that this expectation is operating on. This one already has taken x out because it was right here. So there's no random data floating around there. This one, x has already been taken out, and that never had x in the beginning. So this expectation is only operating on this. So this will be the expectation of EX minus the expectation of EX. And it's going to go to 0. And I'm only left with these two terms. And when I slide my expectation over them, I can recognize them. So let me just write them out. Expectation of EX minus the expectation of EX. Doesn't quite sound right when I say it like that. But be careful where these braces are. And just remind you, this is all being squared. And then I have this other term. And this is going to be the expectation is going to slide over this. Nothing random there, nothing random there. I'll write it out anyway. Expectation minus expectation of EX minus mu squared. There's nothing random in there. It's already been averaged out. But this I recognize. This is the variance of EX. That's what variance is. It's the squared error difference between the thing and its expected value. Plus, in this thing right here is the bias. And it's being squared right there. So this is going to be nothing random there. So that expectation doesn't do anything. And then you have this, the difference between the expected value and the truth. And you're squaring it. So that's the bias squared. So that's kind of cool. Let's just go back over here. We'll just write down what we just learned. The risk function under L2 loss, if you like to say it that way, EX minus mu squared is equal to the variance of the estimator plus the bias of the estimator squared. People always ask me, which way does the bias go? Which one subtracts which? You don't need to worry about it. So we square it out. And that's the right question to ask. Just always ask that. What's negative mean to you? So probably means different things to different people. So this decomposition we've been talking about, that there's two things that are going on in any estimation procedure. Regardless of how you develop that estimator, there's the stochasticity of the estimator, and there's the bias of the estimator. Those are the two things that contribute. And that is always true. I don't care what your estimation scheme is. But when you use L2 loss, you can write this down, and that's kind of cool. That you can just see it in this example that you have some variance and you've got some bias, and this is how they contribute. The bias comes in a squared way. This is already squared in the expectation. So everything's kind of on this quadratic scale. And this is the decomposition. Now, some people take this a little too far. And they'll say, oh, that means that for any estimator, I can reduce the bias or I can reduce the variance. And that's making the assumption that this thing up here is fixed at all times. There's different estimators that can minimize this quantity altogether. But ultimately, there usually is a trade-off like that. That if you end up biasing something, a lot of times you'll reduce variance. And in this specific case, you can see that decomposition. I think that's useful. I'm going to say just one more thing about a couple examples. That if you like L2 loss, you like means. We just saw that right here. And so, kind of like some means. So, if I just think about this, what's the minimizer of this thing? I'll just say what the answer is. You could verify this for yourself, or we can do it in just a moment. Verify when EX, or this is minimized when EX is equal to X bar, the expectation. So if you're dealing with data, if you just had to pick any function, you'd pick that. If you had data, you would approximate that with this. And that's about what we've said. The bias, of course, is minimized when things are unbiased. These are unbiased estimators. These lead to unbiasedness in your estimation procedure. And so I can optimize this without even thinking about that. And when I plug the answer that I get from minimizing this into there, that's automatically 0. That's a very nice thing about normal distributions. Let's just see how we can maybe verify that a little bit more formally. So, when working with data, if, this is a big if you like L2 losses, squared error. I'm not saying you're not going to use that. Just want you to question it every time you do. Seem reasonable? If it does, carry on. But if you don't ask yourself, what are you really doing? So when working with data, you're going to be looking for something like this. So let me just write it out like this. Sum of the xi's minus some function. Okay, this is my estimator. I'm going to try to figure out what it is. It's going to be a function of all of the data. I'll suppress that notation because it might confuse you when I go through and I do the calculus. Divide by n if you want to average. So this is just my empirical averaging right here. So if I'm looking at this, I want to get that thing as close as possible to that. Then I'm going to work with the sample average. How do I know that? I'm going to take a derivative and try to optimize this thing, DDE. Okay, this is really a function of x. I didn't want to overload the notation there. Of this thing right here, We don't care about the n. We're going to set everything equal to 0, and that's going to disappear in a moment anyway. This is just going to be 2 times xi minus e squared, derivative of e with respect to e. There's going to be a minus sign that pops out right there. That's the chain rule. Now what I want to do is I want to find what my estimator is, what my guess is to all of this. So I'm going to set everything equal to 0. So let me just do that in one step. 2xi minus e squared is equal to 0. Better put my hat on everything as soon as I've done that. So I'm just optimizing this. Oops. This is not squared. That is not squared. I brought down the 2 and I decremented. Okay. As soon as I set that equal to 0, that stuff didn't matter. Sum of the xi's is going to be equal to e hat times n. This is a constant over the summing index. So e hat x bar. That's an unbiased estimator. I didn't ask for one, per se. Just kind of threw it into this thing and said, what do you give me? It gave me an unbiased estimator. I get x bar, I want to operate with x bar. I'll give you another hint real quick. If we didn't have empirical data and we knew the full distribution, and you can verify this for yourself, it's the exact same calculus. If we knew the full distribution, fx given theta, and this I didn't presuppose anything. I just wrote down data, asked for a function, it gave me back x bar. If you knew the whole distribution, the optimizer is expectation of x. It turns out to be the exact same calculation that you end up doing. If you're working with data, you'll plug this thing in, x bar. We got a lot of stuff for free in doing that. So we just optimized, came up with x bar, good estimator, that's what I want to use. Central limit theorem applies to that. Boom. Didn't even ask for that. We've got it. It's min sufficient. So it's as small as you can get. It adheres to the sufficiency principle, the conditionality principle, happens to be the MLE. And so there's lots of other stuff you can say. This also meets the Kramer-Rao lower bound. And so, for unbiased estimators. And so I could have optimized and tried to come up with my minimal variance unbiased estimator. X bar seems to have matched that, but I will point out we never asked for unbiasedness when we did this. And so it just fell out that this so happens to be unbiased. That's a little bit of a difference. So what that tells me is without any prior knowledge about anything, it's like I kind of knew something about mu, I can't beat that. And I can quantify things probabilistically using this. So I like to ask people a question, oftentimes. People go through their second year of graduate school, they know lots of math, and I'll ask them, how would you estimate mu in a normal distribution? And they say x bar. They tell me all kinds of things. And almost always they'll tell me, well, I like it because it's unbiased. They'll start there. That's what they learned in Stat 101 probably. But I didn't pick this because it was unbiased here. I just picked it because it minimized maybe something like that. Central limit applies to it. I like that. So what I like to do is ask people after they tell me they like x bar, I say there's lots of other types of averages out there. Harmonic averages, geometric averages. Why don't you like those? They usually pause for a moment. And it turns out they're not as well behaved as this one. And so we keep coming back around to x bar and averages. I just want to point out that you did presuppose this in this analysis of everything. We're going to turn the page next time and we're going to treat this a little bit more Bayesianly. So if that's a word. So I'm going to start thinking about this thing on average as well. And that's what Sierra was thinking about. I remember integrating over theta. Yeah, that's the Bayesian thing to do. And so I need a prior before I can do it. I need to weight, essentially, how I feel about different thetas. I'll give you a heads up and just tie everything together, and then I'll prove this to you next time. If you're a Bayesian and you have a prior, how you want to weight theta and discount theta, how likely you think those thetas are to occur. In the first place, if you like L2 loss, your best estimator is going to be the posterior mean. And so, let me just say this again. If you like L2 loss, you know the full distribution, you'd use the expected value to minimize your losses. If you saw data, you'd use the empirical mean. And what I just told you that I'll show you next time is if you're Bayesian, you would use the posterior mean, and that would be presupposing knowledge or how you want to discount your thoughts about theta. And so that's going to average over both the data space and theta space simultaneously. And so if you like thinking about things in terms of averages and what happens on average, what you might want to do is try to pick the Bayesian estimator that minimizes your losses on average over everything. So Bayesians are really just averages. And so I think that's it for now. So I am going to be asking a little bit about this on the midterm, but don't worry, you're going to have plenty of time to think through these questions. So until then, see you on Friday.